thank you also for this wonderful event and to have the honor to be able to talk here. And there's a lot of inspiring people here, and one of them inspired me to speak in English, because actually English is the language that we normally use when we talk about this stuff at work. So it's actually more difficult for me, at least, to talk about it in Slovak. Okay, this talk is coming from another project that our department is implementing besides for being part of Innovate, which is the EMA project on explainable malware detection. And the motivation for this comes from actually our contact with malware experts, some years back, who observed this very important change in the work in their domain. And that is that there was start to be so much malware samples they need to analyze that it was simply not feasible anymore to do it by just human work, how it was done before, manually. And machine learning gained prominence and is now used in this domain ever since. But the main question which these experts asked was that, yes, and can we trust it? Because the classical application, old school application of some black box systems looks like we have in this schema here, we have some data, then we have some black box system, and then we have yes or no, okay? And this was not satisfactory, at least for our colleagues from Slovak Technical University. And then that's why we started to ask the question if we can do it better in a way that it can be trusted, it can be explained somehow, it can be understood what's going on, and why the answer is yes. So the question that we try to answer is the question why. Okay, and of course, working in such a high-risk domain as malware analysis, also by requirements from the European Union, but we heard this already a couple of times, and from other regulators, we need to take care that we apply AI in a trustworthy and ethical way, so there has to be some human agency oversight, technical robustness, and other condition. This comes from the ethical guidelines on top of which the AI Act is built, and in the AI Act itself, we read that high-risk AI systems, they should be designed and developed in such a way that they are sufficiently transparent and the deployers are able to interpret the system outcomes. And this is basically what we want to do anyway. The interpretability here, however, is understood generally as also understanding the logic and the factors that influence the output. And this is something which we build on heavily in our approach. From the user's perspective, we've probably seen this picture many times because that comes from the DARPA XIA project, which has been implemented some time ago already. And this is also important that if you have a black box system and you have these very smart decisions and AI helpful tools, but if you don't know what happened and why the result is as such, then it's not good for the user. When the user does not trust the system, then they cannot then use the system in their work efficiently and with reliability and trust. So we need to be able to somehow answer these questions for the user. Okay, roughly we can divide the XAA methodology that we kind of decided to apply in this project into 3 categories, and we also already heard today about some of these. And then on the first group is the post hoc methods, which can be applied on top of any black box model. So from this point of view, they are very practical. You can always apply them. You can have a very efficient classifier, and you can apply the post hoc method. But they also have some disadvantages, which are listed here, and I will speak about that in a little more detail. And then we have symbolic methods coming from the symbolic AI, like decision tree learning, concept learning, basically rule learning, where we learn rules. This is a form of explanation the malware expert generally prefer, that what we learned from working with them. And they are very efficient, and but they are slow. Okay? And then there's the issue of fidelity, because since all these post hoc explainers, they typically use some surrogate models to derive the explanations from. These surrogate models can deviate in certain cases from the original model that's being explained, and this is called the fidelity issue. And these symbolic systems, they don't have the fidelity issue, because your formula that you learn, your rule, is also the classifier So the fidelity is always 100%. But these systems are slow, and then there's a third category of coming from the neurosymbolic AI, where this is a promising area everybody is looking into, and here we basically hope that by some combination of the symbolic and the sub-symbolic methods, we would be able to retain the efficiency of learning of the black box models, but we would still have some form of explainability, but this is subject of research, if this explainability is sufficient and how much is it compared to the, say, symbolic systems that we use for that. Okay, so to give you a little bit details, how we worked in this domain is that we work with data that is already available. And this data is available in nicely curated datasets like the very famous Amber datasets or a Sorrel dataset, which had millions of samples pre-annotated, so they're labeled. But these are from the static malware analysis. So here we actually look, we are not running the system, the sample, and we are looking inside. We are analyzing if it imports some libraries and what is the structure of the binary file and so on, and this is how we analyze it. And this has some limitations. But nonetheless, this is generally very popular these days because especially the data is available, and the data comes in this kind of a JSON form. But what we had to do actually in our work is that we paired this with an ontology which we designed specifically for this purpose, which describes basically the domain of static malware analysis. And this ontology, the main goal of this is that we now gain some language in which we can talk about these samples. And the language is universal. No matter which method we use, we can able to express the explanation in the same language, which is very practical for communicating to the expert, to the user, or to compare between themselves. So this was also part of our contribution. And then we actually started to experiment in the area, and we ran a lot of experiments with different kinds of approaches. They are roughly divided in this table based on this key. So on top of we have the post-hoc methods, in the middle we have some symbolic methods, and in the bottom we have some neurosymbolic methods which we used. And then you can basically compare them from the point of view of different attributes, what kind of input they need. So into some of them you can directly feed the knowledge base that comes from the ontological representation. Into some of them you have to vectorize the inputs and so on. The post-hoc methods typically just give you some feature importance information, or some of them can give you some local rules. And with the symbolic and neurosymbolic methods, you get some nicer representation out of that. And we achieved some results basically on this data which we worked for. I don't want to go too much into detail here, but what is important for me is the first column where we see how big a data we were able to process with the method. We know that there's a data set which has 3 million samples. We know that 300,000 samples appear every day in the domain. So if I have a system that can handle 1,000 samples in 2 weeks, or in a week of computation, or 10,000, then it's not so good. But again, even with inspecting such a small number of samples, we were able to achieve some good accuracy measures. So basically, one of the systems or approaches which we use the most is the concept learning, which gives us a very nice benchmark of how the rules could work, and highly interpretable rules. And also after some work, we were able to raise the accuracy, especially the F1 measure, to very nice 93%, which is actually also comparable with the black box method, because these data sets, they are noisy and biased, and even the black box algorithms will not give you like typically 99%. So if you get 93%, it's very nice. And then also neurosymbolic methods achieved some nice accuracies. And I would like to use the remaining time to very briefly tell you a few details. Not so much time anymore. So this is how the output of a post-hoc method typically used. This is feature importance graphic, so-called B-swarm chart coming from the SHAP method. And here you can basically see the individual features of the sample. This is a global chart which shows you the importance through the whole data set. And it is sorted by the most important features are on the top. And so the insight you gain here is you look at and you see, okay, these are the most important features which influence the diffusion. But you cannot really interrelate these features together. So you don't know if you use this feature and that, how does it change this evaluation? Although there's some improvements which my team was able to achieve in basically this combining the features for the analysis. Then we have the concept learning, where it's basically a search through the space of formulas you can construct in some logical language, which typically comes top-down. So we have start with the executable file. This is actually how the representation looks in this ontology. Then we have executable. We're just adding more and more, and we're making more specialized context. And we are searching. It's an infinite search, basically. And there are some systems which you can use. We were able to achieve the time is going down. No, so I actually have more time than I expected. Okay, so I can slow down a little. Okay, so this is how you search through this space. You have a huge space of all rules, basically, expressions that you can construct. And these expressions will be used in the end. If you find a good expression, you take this expression, you can evaluate it against the data, and you hope that it will be true for all the malware samples, and it will be false for all the benign samples. So this is what are you looking for, and it's a very tedious search. And there's a number of systems which you can apply for this. And basically, we experimented with a system called DL Learner, which is like a state-of-the-art system here. And you can see our first results here, where we use these 1,000 samples in the data set. So not very, but this is a slow system, so we had to reduce like this, at least for the initial experiments. And you can see that we achieved the F1 score of 0.72 with different algorithms that are implemented in this system, which is not so satisfactory. So then, what we did, we increased the sample and we were able to improve a little bit more. But in order to achieve this good result, which I presented, 0.93 or something like that, it's actually 0.91 here, is that what we had to do is we had to look inside the data and analyze this domain, and then we figured out that actually the malware dataset contains information about malware families. And you can divide the sample based on the families, and you can create a separate training set. You can train for each family separately, and then you make a big combined classifier. There's some technical challenges here which are hinted on the slide. You have to basically use a much more benign there and just a little malware for each family and so on. Then you make a combination of this, and we were able to achieve this good result with this combination. And it was a lot of learning in the end. It was weeks of computational time with this basically around 50,000 samples processed, which is still a tiny fraction of the overall data available. But for the individual families, like for example, for the civis family, we were able to achieve 0.98. And that's the expression there that we learned. You can read it by yourself. Executable file. It has action enumerate window, and it has at most one action out of the 3 available there, which is kind of interpretable by the malware experts when we ask them. Okay, so what I want to say with this is that this is a very efficient approach in finding good explanations, but it is very inefficient computationally, which motivates us to look into so-called neurosymbolic approaches, and one of those which we tried a number of those, but I just want to present the one which achieved the best result. It's called logic explained network. What is a logic explained network? It's a neural network built on a specific architecture in which you are able to track the logic of the classification from the inputs to the outputs. So you train the network, and then with some pruning and propagation strategies, you are able to extract actual logical formulas which characterize what the network is doing. It's approximation, but not very drastic approximation. The fidelity here is higher than with some post hoc systems. And this is not post hoc. We are reading out the explanation directly from the neural network. Of course, there's challenges, because when we found this system and we actually collaborated with the people who are developing this, they did not apply on such a huge realistic data before as we did. So when we did, and here I want to skip some details, basically what we did is that one of our PhD students went to collaborate with them, and they used some strategies, because when you construct this formula in the end, it's very big. And it's not interpretable because it's too big. It's thousands of clauses. And you have to have some simplification strategy for the formula. And they employed some, but it was not practical for our data. And we managed to improve the methodology by introducing so-called tailored len. Here are the results where the tailored len basically achieves good results and is computationally feasible and produces nice formulas. Here we have some formulas which come out of it, and we also have some commentary of the domain expert. So, and these formulas, as you can see, they are not these nice description logic expressions, but they can be translated. As we have, using the ontology, we can again have this kind of a nice final translation. Something that has a section, and the section has a section feature, which is high entropy, and another feature, which is signature. Something is missing there, I think. It should be signature something. So, again, you end up with some rules. I can say from our experience that the rules, they are not so nice as in case of the description logic classifier of the symbolic concept learner. But on the other hand, we were able to process the whole data set. With the previous version of the Ember, they said it was 800,000 samples. So that was a remarkable achievement. We would never be able to process it with any symbolic method. Okay, so some takeaways. Semantic representation of malware data combined with these explainable methods results in a novel level of explainability, because before you had the post hoc results, you had the feature importance, and now you have some rules, some logical expressions that characterize it. Symbolic methods are very expressive and they give you good result, but they are computationally expective, and neurosymbolic methods are the hope, and we are actually continuing in research, and we are applying different and more refined neurosymbolic methods to see what we can do. Then there's another issue of the data, because as I said, we were working on the static data. But in malware analysis, currently, dynamic malware analysis gain prominence, where you're not just looking into the file, but you are also running the file and you are observing what the system is doing and tracking the data. And we hope that by improving the quality of data, basically we would be able to also derive better explanations. Okay, finally, what about the users? So far I didn't so much mention how this is in the end helpful to the user. So what we have achieved so far in our effort is that we have run a number of experiments with different systems, and we have derived many different forms of explanations in different languages. And now the natural question is, which of these forms are better for the user? Shorter or longer formulas, more expressive, less expressive, how to present to the user. So you can see, for example, how this logical rule can be translated into the sentence in a natural language. And what we do in our project, in the EMA project, which I introduced at the beginning, and we are now actually at the point that we are starting with this, that we want to do some user studies with real human malware experts, because our system is intended to be used by malware analysts, and to see which of these explanations are most preferred. And that will also give us some important feedback on which systems and languages to focus and so on. Okay, thank you for your attention. I hope there are questions.
Ďakujem pekne pánovi Homolovi za veľmi zaujímavú prezentáciu na tému vysvetliteľnosť analýzy škodlivého softvéru. Poprosil by som na ukážku slajdo, či tam máme nejaké otázky.
It's never too late to join.
Predpokladám, že keď sa toto ukazuje, tak nie sú žiadne otázky zatiaľ. Tak využijem možnosť z publika otázku. Máte niekto nejakú otázku z publika?
To je všetko v EME. Ako, naši partneri sú STUčka a Kinit. A tu na mojom slajde, neviem, sa tam už neviem vrátiť teraz, tak my spolupracujeme samozrejme s množstvom zahraničných partnerov, tak máme partnerov napríklad z Talianska, tu máme CNR v Pise, sme spolupracovali, alebo Univerzita v Siene. EMA vlastne, my sme nedostali tú extension nad rámec plánu obnovy, takže my končíme v júni. Že je to taký ambiciózny projekt, ktorý bol pôvodne plánovaný na 4 roky, my ho implementujeme teraz za 18 mesiacov a sme v podstate v polovici. Septembrom sme boli v polovici, takže užívame si.
Nech sa páči, ďalšia otázka.
Hej, na to neviem odpovedať. Viem, že akože tam vo vnútri je tam iná tá architektúra, že musím používať stále tie relu funkcie, ktoré sú akože tiež celkom bežné aj v iných modeloch dneska, ale to je jedna podmienka a potom druhá podmienka je, že keď sa to potom interpretuje spätne, tak sa tam robí nejaký pruning, že niektoré tie menej významné váhy sa zahodia a z nich sa potom generujú tie formuly iba z tých významnejších, cez nejaké cut-offy, ale že či je to obmedzené na veľkosť, to neviem, ale teda zistím u kolegu, ktorý sa tomu skutočne venoval a dám vedieť.
Otázka je nejaký konkrétny príklad využitia praxi?
Hej, nemáme zatiaľ príklad využitia v praxi. My spolupracujeme teda s malwarovými expertami, ktorí sú z akadémie, ale teda máme istú snahu nadviazať aj praktické kontakty, ale zatiaľ sa nám to nepodarilo.
Nech sa páči, ďalšia otázka.
Hej, no je tam veľa tých metód, ktoré môžeš použiť a teda čo my sme použili napríklad to LEN, tak ten trade-off je, že tie formuly, ktoré z toho nakoniec vypadnú, tak oni proste nie sú až také bohaté, ako vyjdú z toho konceptového učenia. Že to konceptové učenie ti dá krajšiu formulu, ktorá je ten malwareový expert, on ju viac ocenil, že sa mu zdala, lebo oni keď im dáme príliš krátku formulu, tak im sa to zdá byť proste, že to je nedostatočný popis toho, že to je také príliš generické. A to boli aj tie popisy, komentáre k tým výstupom ale na tom mojom slajde boli také, že bolo to pomerne generické. Že áno, že odpovedá to nejakému malwareovému správaniu, ale že nie je to niečo veľmi charakteristické, čo ma presvedčilo, že si teraz objavili nejaký nový malware alebo tak. Takže oni si predstavujú tie formuly také dlhšie a to úplne sme nevedeli z toho LN dostať, že všetky tie vysvetlenia boli také pomerne jednoduché. Hoci dosahovali pomerne veľkú presnosť na tých statických dátach. Takže tam je aj tá naša dúfanie k tomu, že tie dynamické dáta, keď budú bohatšie, že dokážeme vlastne tam objaviť nejaké paterny tých správaní, ktoré sú zaujímavejšie pre tých malwareových expertov. V realite, čo mám nejaký feedback, môžem ešte nadviazať, tak máme aspoň nejaké sprostredkované kontakty do jednej významnej bezpečnostnej spoločnosti so sídlom v Bratislave, ktorá je dosť taká veľmi opatrná všetko je veľmi tajné u nich, tak máme sprostredkované kontakty, kde vieme, že oni, tí analyzátori, ktorí u nich pracujú, tak oni používajú rôzne tieto záchytné mechanizmy pomocou strojového učenia, ktoré im môžu proste napovedať nejaké, keď objavujú ten nový malware, hej, na základe možno nejakých behaviorálnych modelov. A potom, keď majú nejaké podozrivé vzorky, že stále ich do vysokej miery analyzujú ručne, že akoby vyfiltrujú si malé množstvo podozrivých vzoriek a tie potom veľmi podrobne pozorujú ručne. Takže my dúfame, že by sme mohli do tejto pipeliny niekde vstúpiť s tým, že by sme vlastne akoby dodali nejaký lepší strednom leveli nejaký automaticky odvodený pravidlový popis toho, čo sa tam deje, ktorý by mohol akoby napomôcť tomu porozumeniu. Ale akože je tam ešte dosť veľký challenge pred nami dostať sa aj na takú úroveň detailov, aby to bolo užitočnejšie. OK, tak dúfam, že som...
Máme tu ďalšiu otázku. Sú tam komponenty, poznatky prenositeľné do iných domén, problémov? okrem malware detection?
Áno, ja si myslím, že celá tá metodika je prenositeľná do iných domén a vieme sú aj iné aplikácie z iných domén vlastne, ktoré napríklad, teraz musím zaloviť v pamäti, ale vo farmakoterapii pri skúmaní nejakých interakcií medzi tými účinnými látkami a tak ďalej. O tom sú tiež také veľké dátové množiny a dá sa tam objavovať takto nejaké súvislosti pomocou týchto symbolických klasifikátorov. Takže tam to bolo aplikované, alebo aj vo nejakých takých tých finančníckych službách, tak tiež tam, kde sú akékoľvek také rozhodnutia nad tými dátami, že ja neviem, že tento klient dostane úver a tento nie, tak to sa tiež dá úplne krásne potom charakterizovať nejakým konceptovým výrazom alebo naučeným pravidlom, ktoré teda zdôvodňuje, že prečo áno, prečo nie. Takže určite sa to ľahko preniesť, celá tá metodika do iných oblastí. Môžem povedať, že my robíme ten malware, pretože tam sú peniaze, zdá sa, akože, že je to akoby... Je to dosť veľká priorita, informačná bezpečnosť aj z pohľadu agentúr, ktoré vlastne financujú výskum, takže máme tam možnosť dobre získať granty, ako je to dobrá skúsenosť z minulosti, viackrát sme dobre pochodili.
Tak ďakujeme pekne, to bol Martin Homola z katedry aplikovanej informatiky.
Ďakujem aj ja.